In this video, we're going to take a look at how we find the gains for our PID control. This process is known as tuning. There are two main approaches to tuning. In approach number one, you start off by creating a model of the plant. The plant is the system that you are trying to control. For example, if we were using approach number one to find good control gains for our motorized potentiometer, we would start out by creating a model of all of the parts that are inside of that motorized potentiometer. Our model would include an equation to describe the behavior of the motor. It would also include any effects involved in the belt that transfers the motion from the shaft of the motor to the slider, and it would also include friction effects. Most of the time, the way you come up with this model of the plant is by doing an actual experiment. Most motion joints can be modeled with just a limited set of basic parameters. Most joints consist of three basic parameters. One parameter that describes the inertia of the joint. Another parameter that describes the joint damping. And a third parameter that describes the joint's spring effects. By performing some simple tests to find out how the joint behaves, we can create a model of the joint behavior. Once we have this model of the plant, that is, the system we want to control, we can then simulate we could create this simulation in any kind of software that we are familiar with, such as MATLAB, or even a more simple modeling software like Excel. Once we create our simulation of just the plant, we can then work in our controller into the simulation. Some software packages like MATLAB or Simulink have built-in simulation tools to add standard controllers like PID controllers into a simulation that we've built of our plant, our system. Or we could build a simulation ourselves by knowing simply that the PID controller works on both the error and also the integral and the derivative of the error. The fourth step in this approach is to adjust the PID gains until we get a good response as calculated by our simulation. This fourth step is actually very similar to the entire approach number two. So I will be going more into depth on what a good response is and how to get those gains for a good response in a moment. For now, this is the approach number one that involves using a model. This is a good approach in the case where you cannot use the actual system to find your gains. For example, if the system you're trying to control is a critical system and you can't afford to accidentally find some bad gains and cause some instability, this is the kind of approach that you would want to use. Now, in approach number two, we do not create a model. Instead, we tune the gains by a sort of intelligent or guided trial by error, and that's the approach I'm going to go into in more detail. This is the kind of approach you would use if you can afford to do some experimentation on the actual system that you want to control. The first step here is to start with proportional gain only. When you start out with proportional gain only, you want to start by setting that gain to a reasonably small value. So how do you determine what is a reasonably small value for your proportional gain? You can do this by understanding what the units are in your feedback control diagram. Let's take a look back at the simplified feedback control diagram that we've been using in these videos. I'm going to expand this diagram to include our controller, which at this point in our tuning process is just a proportional controller. Here I've expanded the diagram to show our proportional controller. I want you to notice what the input and the output of this controller are. The output of the controller is the input to the motor. That means that the units on the output is voltage. Now, what are the units on the input? The input here is the error. This is error in positioning because we're doing position control. So the units on this error will be position units, something like millimeters. Because the input to the controller is in units of millimeters and the output of the controller is in units of voltage, the value Kp is a kind of unit conversion that converts millimeters into voltage. In other words, Kp has units that are something like volts per millimeter, or this may be different depending upon what your position error is measured in. If you're doing a rotational position control setup, then this might be volts per degrees of error. In order to find a reasonably small value for Kp, you have to think about what are the maximum and minimum limits that your system might have on these two units. For example, the voltage input to your motor might be limited between, say, 0 and 9 volts. That would be a reasonable limit for our slide potentiometers, for example. But your motors might have a different voltage limit. Now, think about the range that the denominator might have. How many millimeters of error might be detected in the system? For example, our slide potentiometers have a position range between about 0 and 100 millimeters. So the maximum error in our case is about 100 millimeters. I need to start out by choosing a value for Kp that will not produce a voltage greater than 9 volts when the error is at its maximum, 100 millimeters. In other words, I should not set a Kp value that is greater than 9 divided by 100. This is how we can find a reasonably good starting value for the value of Kp. Now, let's take a look back at our approach. Step number 1 was to start with only proportional gain and to calculate a reasonably small gain. We've already done this step in this example. Step number 2 is to use this small proportional gain and watch the response as you send a position command to the joint. In other words, we want to watch the positioning response with the small Kp value. Let's take a look at what that positioning response might look like. It's a little bit difficult to make the connection between what the time response looks like and what the actual physical behavior of the system looks like as you watch it. But you will become better at this as you practice it, and we'll practice doing this several times in lab. For now, I'm going to show you what the time response looks like and what we would do in response. So I'll make a time response where the x-axis is time and the y-axis is position. And in our example, this position would be in millimeters. Now here we have some commanded position, and we would have some response position, the actual motion of the joint. With our small kp value, it's likely that the response we see would look something like this. With a small kp value, it's likely that we would see a large steady state error, no overshoot at all, and a very slow rise time. In our tuning process, our next step is to slowly increase the value of kp to speed up the response, reduce the steady state error, and, unfortunately, probably increase the overshoot. So up here, step 3 is to slowly increase the kp value. As we slowly increase the kp value, we will see 3 effects occur. We will see a decreased rise time. In other words, the response will get faster. We're also going to see an increase in overshoot. And thirdly, we're also going to see a reduction in the steady state error. Now, reduction in the steady state error is a good thing, and decrease in the rise time is also a good thing. But an increase in the overshoot is a bad thing. What we're going to do is we're going to increase the kp value slowly until the overshoot becomes more than what we are willing to accept for our particular system. Once we've increased kp enough that the rise time has become as low as possible, the steady state error has become as low as possible, and the overshoot has just exceeded the amount that we are willing to accept in this system, we now have 3 options of what we could do next. Option number 1 is to stick with the controller that we have. It might be that the response we've achieved with just proportional control is sufficient for our application. If the response is okay, we don't have to go on and add derivative or integral control. We can stick with just proportional control and use the gain that we just found. The other possibility here is that the response is not okay. If the response is not okay, there are 2 ways it might be not okay. Either the rise time is too big. In other words, the response is too slow. Or the steady state error is too big or too much. In this case, you would want to change your controller by either adding derivative or integral control. There are 2 different ways you can address this problem of having a too slow response or the steady state error being too big. One approach is to simply add integral gain. The other approach is to increase kp and simultaneously add derivative control. Now, how do you decide which of these approaches is better? The way you figure this out is by being familiar with the effects of each of the 3 gains, kp, ki, and kd. This takes a little bit of trial and error and watching the response as you try different gains. But let's take a look at what the effects are of each of the 3 PID gains. We've seen each of these effects individually in previous videos. I'm just going to summarize those effects here. Knowing this chart and remembering the effects of each of the gains will help you in your process of tuning a controller. Here I've shown a chart where we can record the effects of KP, KI, and KD on each of the three effects that we want to have on the time response: the rise time, the overshoot, and the steady state error. I'll use arrows up and down to represent what happens when you increase each of these gains. When you increase KP, the increase of KP causes the rise time to go down. That's a good thing, so I'm going to show a down arrow drawn in green. In other words, it has a good effect of decreasing the rise time. Increasing KP also has the negative effect of increasing overshoot. So I'll draw a red arrow pointing up for this one. Finally, increasing KP also decreases the steady state error, which is a good thing, so I'll draw a down arrow in green, representing the good effect of decreasing steady state error. Increasing the integral gain also has the effect of decreasing the rise time. And it also has the negative effect of increasing overshoot. In fact, sometimes adding integral gain can actually make a system go unstable. So you really only want to use it for the purpose of decreasing the steady state error. Now, KI does not only decrease the steady state error, it actually gets rid of steady state error altogether. I'm just going to put the word eliminate in this box to show that KI does not only reduce the steady state error, it can make the steady state error go away altogether. Finally, what are the effects of derivative gain? Derivative gain has not very much effect at all on the rise time, so I'll just put a dash there to indicate that it has no effect. It also has little or no effect on the steady state error. The only effect that it has that is very useful to us is that it decreases the overshoot. That's why in our flow chart that we drew previously, we represented one possibility for improving the response is to increase both KP and KD at the same time. Can you see from this chart why that combination would improve our response? As we increase KP, we would get the two beneficial effects of reduced rise time and reduced steady state error, but we would also cause the negative effect of increased overshoot. However, if we couple that by increasing KD at the same time, KD can reduce the overshoot and compensate for the increase caused by the KP. KD has no effect on rise time or steady state error, but by combining it with an increase in KP, we can achieve an overall better response. This process of changing gains and watching the response until we get a good, desirable response with a fast rise time, low steady state error, and low overshoot is much of a trial and error process. Even if you take the first approach, which involves modeling the system, we still have to go through a final step of adjusting the PID gains in order to get a good response. So this process of trying different gains and watching the response is a kind of a skill that you would develop as a motion controls engineer. For our robot joints, the kind of response that we want is very much the same as any other motion control applications. We need our joints to be accurate, in other words, have low steady state error, we need them to be very stable, that is, have low overshoot, and we also want our joints to have a fast response, that is, have a low rise time.